Yeah, maybe before the lunch break, we can have maybe some part of this covered. It's a security detection and verification for smart contract. And we're going to talk about like risks of smart contract and security detection tech, formal verification tech, and security practice. So why smart contracts are a risk? First, defects are hard to fix, and the code is open source and public. Everyone can read the code and find bugs, and some of them might be malicious, and it has high values at stake. And also, blockchain platform and smart contract language is constantly developing and trying to be more mature, and there are bugs that's in this process. So this is other examples of yesterday's vulnerabilities, and also there's also complex financial interactions such as flash loan attack, which we didn't cover, but one of the Oracle problem have this financial interaction that's kind of complex. You can borrow assets and change the price. Security detection tech. Security audit and detection tools fill the gap between developers and security experts. First, we just do like static analysis and scanning. It is fast, but it's prone to false positives. And then we have this dynamic analysis and testing that is precise, but prone to false negatives. So if you didn't find bugs in this dynamic testing, that doesn't mean that your contract is safe. It just means the dynamic testing is not enough, and the coverage might need improvement. There's also a formal verification that is rigorous, and we can prove correctness, but it is a little bit slow. So this is the security audit pipeline. First, we develop the code, and then we test the function, and then we use this static scanning. Usually, it's just one click, and everything will be automatic. And then we do fuzzing and formal verification. Fuzzing and formal verification is complementary. You will not replace fuzzing with formal verification because of other limitations that we will mention later. Now we have this on-chain development. So here's a diagram of the effect of each testing method. Security audit can find some very unique bugs that you would not find by using other tools, because you have to understand the business logic and other parts of picture, not just the contract itself. The static scanning they can find some basic bugs, but a lot of other bugs will be omitted, and that's why it's not enough to just use a scanner to scan your contract before deployment. Formal verification and fuzzing is like this, but actually fuzzing has some bugs that formal verification cannot find because of the limitations. This is just in theory. Formal verification, if implemented perfectly, then it definitely can stop basically all the bugs that fuzzing can find. The formal verification provides complete coverage of all boundary conditions. It proves that the actual execution of the program meets the expected behavior. So that's why it's superior than just testing. But there are constraints of formal verification. That is non-linear computing. That means the execution flow will have countless paths, and maybe it's not exhaustive. And also there's solving timeout. We don't want to wait too long for formal verification to finish. The solver will give timeout error. And also state space explosion. So if there's too many state space, then the formal verification will not be sufficient enough. So that's why, in theory, fuzzing formal verification can find all bugs that fuzzing can find, but in practice, there are still some bugs that you can only find through fuzzing because formal verification technology is not perfect. Any questions? Yeah. Yeah.
What is fuzzing exactly?
Fuzzing is you feed the program with random inputs, generated inputs. You use like a corpus, like you generate like very distinct inputs, and then you just feed this program and make it run and get the output. And if the output is wrong or is unexpected, then it's like an edge case that you need to consider. Yeah. For example, the famous fuzzer is like libfuzzer, and Google's team, they use this libfuzzer to find a lot of zero-day bugs in different programs. So not just smart contracts, but other programs as well. You can use fuzzing to find bugs. Yeah.
So on the formal verification, you say it's slow, right? How slow can it be, or would you even know whether you terminate, right? You may not know, right?
It is not slow, but I mean, like it's still up to people who use the formal verification because they are solving timeout. That means if you consider like all the cases, the time goes to infinite, and that means like you only care about the variables that's most important to your business. Yeah. So in a regular testing, formal verification always have a time, like it will finish under a certain amount of time, but it's not exhaustive. Yeah.
Thank you.
Yeah, so this is the formal verification technology. We want to know that what the code is supposed to do, but not how. So we'll basically make sure that the code will behave as in every circumstance that we make it, we want it to be. And there's also we make sure that the desired properties in math logic will be met. So we'll talk about the details later. Okay. Why is the launch break? I think I paused it. 12 o'clock. Already paused it? No? Oh, it's okay?
Yeah,
Okay.
okay.
Sure. Yeah. Yeah. So let's talk about some math. Here, we have a simple function of transfer. It's a really basic function in solidity. And what we want to make sure is that certain requirements need to be met. After the transfer operation, the target account should have an additional amount, and the source account should reduce amount. So that is always should be the case. That's not supposed to change. So for example, this is a test that we can write. From Alice to Bob, the amount is 10, and this works. This works exactly as we expected. But this does not mean that this contract has no bug. It's just a test. It shows that how this function works, but not supposed to work, like always will work. We just give it like random numbers, like the amount is 10 and the old balance is 30. So it's just a test case. Now, how do we make sure that these properties can be met all the time? Yeah, so test is simple, no issues are found. And when we do fuzzing, that means we give it lots of input and trying to find out what might went wrong. So we give it numerous test cases. And our Beosin vars actually have the fuzzing capability. And, but numerous is not complete. Fuzzing can still behave badly under time constraints. And that's why we need formal verification. And we see those weird signs, and they are basically properties that we make sure that they exist. The requirements are always met at the same time. So this is the science of formal verification. And just to come back to this code, in fuzzing, this bug can actually be found. But in fuzzing and the formal verification, this bug can actually be found. So can you guess? Can you guess where's the bug at in this code? Sorry?
The spelling is wrong. U-I-N-T should be unit.
Oh.
Fourth line.
Fourth line?
First line.
First line, okay, first line. You in? Oh, yeah, sorry. It's you, okay. Oh, I can't change the picture. Sorry. You mean the uint?
Yeah.
Yeah, sorry, this is a picture, so I can't change it. Yeah, but this contract actually has a bug, so yeah. Can anyone tell what bug it has?
I think it's a number overflow.
So what if the from and to address is the same because it's passed in by user, right? So basically, if Alice is transferred to Alice, if Alice is transferred to Alice, then the old balance of Alice will be 30, and the new balance of Alice will be 40. Yeah. So basically, Alice got money for free. If he transfer money to himself, then he will get money for free. So basically, this allows an exploit case. Basically, people can mint assets infinitely. But if you just do simple testing, that's not going to work because you assume that from and to are different. And that's why fuzzing is important because fuzzing is, they are not like people. They don't assume things. They put in different things. They put in different scenarios. And when you put in from and to both the same address, then you see that this formal specification will not work anymore because you get more assets later than before. So this bug could be found in both fuzzing and formal verification. Yeah, testing can only prove that the program has errors, not that the program is error-free. And here's the formal reasoning. We always have this P and Q, and C is the execution of the contract. So it's almost like solidity state machine. P is the precondition, and Q is the post condition. And this is the reasoning process of how formal verification acts on this piece of code. And we know that the old balance, we follow the code flow. The old balance from is equals to balance from, and old balance to is equals balance to. This is the precondition, the precondition, and that's the post condition. Post is a new balance. And the thing in the middle is C, is execution process. Yeah, so when you have this intermediate execution process, we can use a solver to solve different paths. And then we have to make sure that every path meets the conditions of this property. So that's why formal verification is strictly based on what requirement you write. If your requirement written is not, the coverage is bad, then maybe some bugs will be overlooked as well. So security practice, static scanning. We scan contracts for common vulnerabilities, and we use like one-click automatic scanning for that purpose, and then we can export a report afterwards. And for formal verification, we prove the program is error-free. The hardest problem is computational, so it's always we have to write specification with the consideration that our computational power is limited. So smart contract security is a systematic project. It requires professional security teams to study safety issues, summarize security rules, and security attributes. We develop security detection and verification tools and conduct security audits. In practice, the most important is finding bugs, and the hardest problem is valuable specification. So writing specification is a big topic. And I think that in the future, there might be like templates in writing verification just to make sure that there's a standard in formal verification. So this, from this method, we can improve the quality of security audit. Yeah, we use a hybrid detection system. After we put this specification and source code into a file, then we run it through our VAS product. And then our VAS product will do fuzz. And if there's any rare behavior that violates the spec, for example, the front and to address the same, we will output that and make a bug report. So another practice is the security property invariant. The invariant exists for the purpose of maintaining resource integrity. For example, a limited supply. Like if there's for example, an underflow vulnerabilities and there's suddenly huge amount of assets being minted, that violate the invariant, which is a limited supply, and authorized operation, that is permission control. To do that, we have to maintain the resource and limit the currency supply, and only authorized users can perform operations. So this is a game of battling. Yeah, so the power of two wizards can only be transferred to each other, and the total amount cannot be increased or disappeared. So power, the power has to maintain the same, and that's our security property invariant. To write it in math, it's just wizard power plus wizard 2's power equals the old power. So no new power is generated in this code. That should be the specification. But same issue here. There's an error here. So can anyone guess? It's the same bug, actually. Like, what if the user battles himself, right? So the power actually increases. So it's the same in the game industry as well. Yeah, so afterwards, we fix this code by require, like, you can't just fight yourself. Wizard ID 1 is not equal to wizard ID 2. Yeah, and another important part in formal verification is that we can put in, for example, the K variant to make sure that the swap model is sound. As we mentioned before, the K value should always be bigger after the swap. So that is an invariant that you can put in the equation. When user intends to exchange two tokens, Uniswap uses the constant product formula, the K, to determine the transaction price. So this is a constant product formula. And we mentioned before that the delta X and delta Y is the new, it's a change. It's a change in the process. So the users use X to swap Y, and that's why the X is increased and Y is decreased. And the K is the new value, And we have to make sure that this new value is bigger than the old value. Yeah. So when there's fees, then it must be bigger. And there's also a security property invariant. For example, the total ledger integrity. 2 token reserves after swap should always be greater than the reserves before the swap. So there must be a token that is bigger than the previous amount in the reserve because one amount is being sent in. So that's also a security property specification. And if we use that in the bridge, that means, for example, after the user burned the synthesized assets, then the total amount is the same. So the user withdraws and burns the amount of synthesized assets. Like one has to increase and one has to decrease, but the total amount is the same. Yeah. So this is we write in the proof, and this is what we use in fuzzy. And the workflow goes like that. So first we do the static scanning, and then we do fuzzy, and then the last is formal verification. But it's like a feedback loop. Like after we write verification, then we still do fuzzing, trying to find edge cases. So yeah, let's take a break, and we'll come back after lunch.
Jasper, allow me to say a few words.
Yeah.
Thank you. For those of you who don't know me, I'm David Lee. But I would like to thank Jasper, who flew in all the way to Singapore, and I'd like to thank Beosin. This is organized by the Blockchain Security Alliance, of which Beosin is the lead together with SUSS NIF, supported by NUS and many other Web3 companies. So we will continue to have no more courses, but Jasper, this is the first time you're teaching.
Oh, it's first time.
Yeah, but I think he has done a fantastic job, and from the questions and so on, you can see the amount of experience that he has and the kind of knowledge he has about what has happened in the market. Because every time where there's a hack, the Security Alliance is triggered, and we need to find out what is happening, and expert like Jasper will help us to solve the puzzle of where those money has gone and how to trace them. But the fact that a lot of us have been teaching for many years here, never have we done any class as good as this, especially this first time. So I would like you to put your hands together to thank him very much for this morning, which we really enjoy a lot about this. Please put your hands together and thank him.
Welcome back, everyone. And just a follow-up on the lecture before, we were talking about a hash collision. And this is an example of what the attacker did in a poly network hack. So the original function that is allowed is this really long function, put cur epoch com public key, that has this signature. This is a 4-byte function identifier. And what the attacker did is he brute forced a string that if set as the method in the code snippet, if it's set as the method, then it has the exact same hash string. So we can see the attacker's function identifier is exactly the same, but his function is very weird. It's like F1121318093, almost like a telephone number, but obviously it's just a random string, but happen to have the same hash. This confuses the cross-chain manager when attacker called this cross-chain transaction from Ethereum network to the Poly network. And so therefore, the ETH cross-chain manager thinks that the attacker was calling this put cur, the legitimate function, within this contract data. Because this function is only callable by this manager contact. Therefore, the attacker's public key is registered as keeper. Afterwards, it'll up to attacker's will to change other parameters of contract and steal funds. This process was repeated for other network, and in total, 610 million USD was stolen. Yeah, so this is another example of the cross-chain bridge hack.